Hello everyone. In today's session, we are going to learn about convolutional neural networks, commonly known as CNN. CNN are one of the most important deep learning architectures used for image processing and computer vision. They are widely used in applications such as image classification, face recognition, object detection, medical image analysis, autonomous vehicles, and many other computer vision applications. In this presentation, we will understand what a CNN is, its architecture, convolutional layers, filters, stride, padding, pooling layers, activation functions, fully connected layers, and finally, how all these components work together to produce a prediction. Let us first understand what a convolutional neural network is. A CNN is a deep learning model specifically designed to process grid-based data, especially images. An image can be represented as a grid of pixels. Each pixel contains information about color or intensity. The important advantage of CNN is that they can automatically learn useful features from these images. The learning happens hierarchically. At the beginning, the network may learn simple features such as edges and lines. As we move deeper into the network, it learns more complex features such as textures, shapes, and objects. The architecture is inspired by the way the visual cortex of the human brain processes visual information. Because of these properties, CNN have become a fundamental architecture in modern computer vision. Now let us look at the overall architecture of CNN. A CNN processes an input image through a sequence of layers. The input begins as raw pixel information. The first convolutional layers detect simple features such as edges. As the information moves through deeper layers, the network learns increasingly abstract representations. Say, for example, an early layer may detect an edge. A later layer may combine those edges to identify a shape, and an even deeper layer may recognize an object such as face or a vehicle. Therefore, we can think of CNN processing as a journey from raw pixels to high level semantic features. Each stage contributes to transforming the original image into a representation that can be used for the final prediction. There are four important components in a typical CNN. The first is the convolutional layer. It applies filters to the input and extracts features such as edges, textures, and patterns. The second is the pooling layer. Pooling reduces the spatial dimensions of the feature maps while retaining important information. The third component is the activation function. Activation functions introduce non-linearity, allowing the network to learn complex relationships. Finally, we have the fully connected layers. These layers combine the features learned by the earlier layers and use them to make the final prediction or classification. So, in simple terms, convolutional extract features, pooling reduces dimensions, activation introduces non-linearity, and fully connected layer perform the final reasoning. Now let us understand the most important component of a CNN, the convolutional layer. A convolutional layer uses a small matrix called a filter or kernel. This filter slides across the input image. At every position, the values in the filter are multiplied with the corresponding pixel values. These multiplied values are then added together to produce a single output value. As the filter moves across the entire image, it produces a feature map. Different filters can learn to detect different features. For example, one filter may detect vertical edges, another may detect horizontal edges, and another may detect textures. An important advantage of convolution is that it preserves the spatial relationship between pixels. Another important concept is parameter sharing. The same filter is reused across different locations in the image, which greatly reduces the number of parameters compared with a fully connected network. Let us now look at the important parameters of a convolutional operation. The first is the filter or kernel. It is a small matrix whose values are learned during training. The filter extracts specific features from the input. The second parameter is stride. Stride determines how many pixels the filter moves at each step. If the stride is increased, the filter moves faster and the resulting feature map becomes smaller. The third parameter is padding. Padding means adding zeros around the border of the input image. There are two commonly discussed types: valid padding, where no padding is added, and same padding, where padding is used to maintain the spatial dimensions under the usual stride minus 1 setting. Finally, an activation function, commonly ReLU, is applied after convolution to introduce non-linearity. These parameters determine how the convolution operation transforms the input image. After convolution, CNN commonly use pooling layers. The main purpose of the pooling layer is to reduce the spatial dimensions, the width and height of the feature maps. This process is called downsampling. Pooling reduces the amount of computation while retaining the most important information. It can also help control overfitting and provides a degree of translation invariance, meaning small shift in an object do not significantly affect the resulting representation. There are three types shown in this presentation. The first is max pooling. It selects the maximum value from each region and therefore retains prominent features. The second is average pooling. It calculates the average value of each region and captures overall feature information. The third is global pooling. It reduces each channel to a single value and is often used before fully connected layers. Activation functions are also very important in CNN. After a weighted sum or convolution operation, an activation function is applied. Its main purpose is to introduce non-linearity. Why is non-linearity important? If we remove activation function, even a very deep neural network would behave essentially like a simple linear model. Such a model would not be able to learn the complex relationship present in real world images. Activation functions allow the network to learn complicated patterns. The general process is: first, the input is multiplied by weights, then a weighted sum is calculated. Next, an activation function is applied. Finally, the activated result is passed to the next layer. This repeated process allows CNN to learn increasingly complex representations. Now let us look at the common activation functions used in neural networks. The first is ReLU, or simply we can call it as rectified linear unit. Its formula is A of x equals maximum of 0 and x. ReLU is very popular in hidden layers because it is computationally efficient and helps reduce the vanishing gradient problem. The second is a sigmoid. Its output ranges between 0 and 1, making it useful for binary classification. The third is tan H. Its output ranges from -1 to +1, and its a zero centered output can help learning in some situations. Finally, we have softmax function. Softmax is commonly used in the output layer for multiclass classification because it produces a probability distribution across the different classes. Therefore, The choice of activation function depends on where the function is being used and what type of problem the network is solving. Now we come to the fully connected layers, also called dense layers. These layers are typically found toward the end of CNN. The convolutional and pooling layers are mainly responsible for extracting useful features from the image. The fully connected layers taken these learned features and use them to make the final prediction. In a fully connected layer, every neuron is connected to every neuron in the previous layer. Before connecting the feature maps to the fully connected layer, we usually perform an operation called flattening. Flattening converts the third dimensional or three-dimensional feature maps into a single one-dimensional vector. This vector is then provided as input to the fully connected layers. The network can then learn complex combinations of the extracted features and perform tasks such as classifying an image as a dog or cat. Now let us put all the components together. First, we provide an input image to the CNN. The image is represented as a grid of pixel values. Next, the image passes through the convolutional layers. The filters extract important features from the image. After convolution, an activation function such as ReLU introduces nonlinearity. Next, the feature maps pass through the pooling layer. Pooling reduces the spatial dimensions while retaining important information. Finally, the extracted features are passed to the fully connected layers. The fully connected layers combine the learned features and produce the final prediction. So, the overall flow can be remembered as input image, convolution, activation, pooling, fully connected layer, then prediction. This sequence form the basic foundation of a CNN. Let us summarize today's presentation. First, CNNs are specifically designed for visual data, especially images. Second, CNN learn features hierarchically. Layers learn simple features such as edges, while deeper layers learn complex patterns and objects. Third, the different layers have different responsibilities. Convolutional layers extract the features. Pooling layers reduce the spatial dimensions. Activation function introduce non-linearity. Fully connected layers combine the extracted features for final prediction. Another important advantage of CNN is efficiency. Convolution uses parameter sharing, while pooling reduces the spatial dimension. Together, these design principles make CNN powerful and computationally practical for processing high resolution images. That's all about today's presentation. Thank you.